Alright, so now that we know how to come up with Taylor and Maclaurin series for things, expansions, the final step is to approximate the value of a function by using these things. And that's kind of what it's all about. The whole idea is they can come up with, a number like, what's e to the 2.1, if you wanted to know that, like you're working some population growth word problem or something. You might want to know what e to the 2.1 was, but you didn't have a calculator on you. So you could easily, in the course of like half an hour of painstaking multiplication by hand, come up with e to the 2.1 by using the Taylor series approximation of e squared, with these factors thrown in to kind of fudge it up to 2.1, as we discussed in the previous couple of videos. So right here I've got the approximation, the Taylor series expansion of e squared, or e to the x, about 2. So what we're saying is that, hey, if we took the graph of e, which crosses at 1 and goes up like that, what this series represents is if we started with this point and then kind of, this sort of formula represents a polynomial that kind of has a similar shape and everything to the exponential at this at 2. They touch each other. There's a tangent right at that moment, and they stay pretty close in that neighborhood. So if you wanted to just plug in 2.1 to this thing and multiply it out by hand, you could get a pretty good approximation of what the actual curve would be at 2.1. So of course the first big step in these things is picking a good value to center my series around. So if I wanted to estimate e to the 5.6, or better yet, e to the 5, if I wanted to estimate e to the 5.1, do I want to use my e squared one, or do I want to use e to the 5th? I want to use something close to the value that I want to find, because the closer if I center my series at 5, that's really close to 5.1, so that's good. But I wouldn't want to use my Maclaurin series of e to approximate e to 5.1, because 0 is so far away from 5.1 that those two curves could be really far off by the time we get out there, so I could have a big error. So I'm much better off using a curve that's tangent right near the value I want to actually calculate. And you might think it's lame that when we're approximating e to the 2.1, we've got e squared in the equation. But I think you'll agree, e squared you could come up with in a pickle if you had to. If you looked up e and you knew that it was 2.7, whatever it is, you could multiply 2.7 times 2.7 by hand and then literally calculate this polynomial's value at 2.1. By hand. It would take a while, but that's better than nothing. And in a time before calculators, when all this stuff was invented, that was actually pretty cool. You'd be able to find e to the 2.1, with some accuracy. All right, so let's take a crack at it. Let's find a third degree approximation of the natural log of 1.1. So third degree approximation, that's just telling us, hey, let's take out the Taylor series to a power of 3, so to the x cubed term, which means I'll actually need one more term than is here, but that's no big deal. And we're trying to approximate the natural log of 1.1. So what's a number near 1.1 that I know the natural log of, like I know the exact value of? And that would be the natural log of 1, right? So the ln of 1 is 0. So that's actually the x-intercept of the natural log function. So I think what I should do is I should find the Taylor series expansion for natural log about 1, and then I'll plug into that to approximate the natural log of 1.1, which is pretty nearby. All right, so we're going to use f of x is just going to be natural log of x, obviously. And then c is going to equal 1, because we're finding the series about 1, since I happen to know ln of 1 off the top of my head. So first things first, we need a bunch of derivatives here. F prime equals 1 over x. F double prime is going to be negative 1 over x squared. And f triple prime is going to be positive 2 over x cubed. I think that's all the ones we need, because the third degree Taylor expansion has a power of 3. F triple prime is the highest prime we got. All right, so ln of x, we're going to say is actually equal to f of 1, so natural log of 1, plus f prime of 1, which would be 1 over 1, times x minus 1, plus f double prime of 1, so that's negative 1 over 1, over 2 factorial times x minus 1 squared. And I need that cubic term, which is triple prime of 1. It's going to be 2 over 3 factorial x minus 1 cubed. All right, so ln 1 is 0, so that term goes bye-bye. So ln of x equals, don't need that 1 really, so we got x minus 1. And I'm going to leave that in parentheses just because there's so many x minus 1s that whenever I see an x minus 1, might as well just leave it in parentheses. Should have written it down a little bit lower so I don't get in the way of this stuff over here. So we got x minus 1. So that's negative 1/2 x minus 1 squared plus 2/6, which is 1/3, x minus 1 cubed. All right, so x minus 1, now what is x? Well, at this point, anything I want to plug into x, I can plug in, and that's going to be approximating the natural log of that same number. So if I want to find the ln of 1.1, I just need to plug in 1.1 for x, and x, and x. So I got 1.1 minus 1 is 0.1, minus 1/2 times 0.1 squared, plus 1/3 times 0.1 cubed. And now you can see why it's nice to leave this x minus 1 in parentheses, is because that just becomes 0.1 just like all these others did. So the physical meaning of that 0.1 is that if you look at the graph of this thing, we know that the natural log crosses the x-axis right there at 1, and then what we were trying to find was the natural log of 1.1, which is like right here, right? So we're trying to find the value of that point. So what the 0.1 represents is the x distance between the point we know and the point we want to find. That little distance is 0.1 in this case. So that's why 0.1 shows up in our approximation. It's like saying, hey, rise over run to the right by 0.1. Then this term is sort of accounting for the second derivative, that little bit of curvature, that negative curvature, etc. All right, so now if you work all this out, you get something like 0.0956, and that is our approximation of natural log of 1.1, and it's third degree because we went up to a power of 3 in our Taylor series. Now, if you don't say what degree it is, technically the Taylor series goes on forever, right? So we could come up with a 10th degree, 20th degree, but what you'll find is if you actually plug in the numbers, and we'll do that in a second, that usually your second degree term is already very accurate, and your third degree is just going to be crazy, like out to many, many decimal places of accuracy. All right, so this time we'll do the P5, meaning the 5th degree approximation of the sine of pi over 12. Now, if you watched a previous video, you saw that the Maclaurin series for sine is really simple. And I would argue we should probably use that. I'm going to go ahead and derive it here again because I want to get us in the habit of seeing that's easy to do. But the question is, why would I even use the Maclaurin series? So, the first thing we want to figure out is that if I'm trying to approximate the sine of pi over 12, which is not one of our unit circle angles, it's kind of a funky one. But if I want to approximate pi over 12, I should try and think of a unit circle angle that's pretty close to that in order to do the approximation. Now, pi over 12 happens to be halfway between 0 and pi over 6, which is 30 degrees. So which one am I going to pick to do my series around? If you pick 0, you are correct, because what's great about the Maclaurin series for 0, or for sine, the sine of 0 is 0, so a lot of terms drop out, and that's why we want to use that one. So f equals sine x. So I'm going to center this around c equals 0, which means this goes bye-bye, this goes bye-bye. F prime equals cosine x. F double prime equals negative sine x. F triple prime equals negative cosine x. F, oops, just 4, equals back to positive sine x again. And then since I'm doing P5, I need the fifth one, which equals cosine x. All right, so sine x, and this is centered around 0, which is pretty cool. So equals f of 0, so sine of 0 is just 0, plus f prime of 0, so cosine 0 is 1, don't need, times x, plus f double prime of 0, so negative sine of 0, oops, that's 0 again, so this term drops out. So now I need f triple prime of 0, which is going to be negative 1 over 3 factorial x cubed. Now my fourth degree term has a bunch of 4's in it, so it's got the fourth derivative. Oops, the fourth derivative, so sine 0 again is 0, which means the fourth term goes away. So now I've got my fifth degree term, which is quintuple prime, f5 prime or whatever. Cosine of 0 is 1, so I've got 1. My denominator, since we're on the fifth term, is 5 factorial, and x to the fifth also has a 5 in it. All right, so this is our fifth degree approximation, our fifth degree Maclaurin series for sine x. And now all I got to do is plug in pi over 12 to the mix. So if I want to find this, if I want to approximate the sine of pi over 12, all I got to do is plug in pi over 12 everywhere I see an x. So it's pi over 12 minus pi over 12 cubed times 3 factorial 6 plus 1 over 5 factorial, which is, I believe, 120 times pi over 12 to the fifth power. Now you might be thinking this is an awfully big mess, and you'd be right, but you can plug this into a calculator. The one and when you do that, you get 0.259. Now there's two things I want to caution you. One is you want to have your calculator in radian mode. Why is that? You know what? You don't actually have to have it in radian mode for this particular problem, but usually what happens on these problems is you'll want to type in the actual value to see how close you were, because a good way to check your answer is to type in, sine of pi over 12 to your calculator and find out what the actual sign is, and just make sure your approximation is very close to that. And when you do that, you better be in radian mode, because otherwise you're going to get a wacky number, like really close to 0 probably, because pi over 12 degrees would be like way less than a degree, so the sign would be really tiny, like almost 0 instead of 0.259. But pi over 12 radians is 15 degrees, which, a quarter looks about right, because that's about half the sine of 30, and pi over 12 is about half of 30 degrees also. Cool beans. And one other caution is that when you plug in pi, you really do want to use pi in your calculator out to many digits. If you just do 3.14, what will happen is these are very accurate. So this approximation, even though we only went to the fifth term of the approximation, that's going to be really accurate out to many decimal places. So if you plug in 3.14, that'll actually create more of an error. If you don't use all the digits of pi, that'll create a bigger error than the fifth term is actually generating. So the fifth term is going to be accurate out in like fourth and fifth decimal place. So by plugging in 3.14, you have way less sig figs than the Taylor approximation is capable of delivering. And that's what's kind of weird about Taylor approximations, and Maclaurin series also, is that they're really shockingly accurate. So and we're going to see that in a second, but if you get into the third degree term, you're really getting out to many, many decimal places. All right, so that brings us to a topic which is sort of a subset of these, which is talking about the error in the approximation. Now this is a trick that only works for alternating series. So recall, in the previous chapter we talked about alternating series was one of the many types of series we talked about. And it turns out that when you have an alternating series, you go, you start with a value, then you take away some, then you add some, then you take away some. And as you go further and further along that series, the terms get tinier and tinier, right? So you're kind of like, homing in on the exact value as you go further and further into the series. If we look on a number line, what's going on is if this was like the real value, the exact value of something, your first approximation might be over here. Then you add a term to it, and it goes over to here. and then you add the next term to it, but it's alternating, right? So your next term, when you add the next term, you're actually taking away. So you jump back over to here. And then when you add the next term, maybe that one's positive, so you end up going to the other side of real value. And what you do is you hopscotch back and forth, getting closer and closer and closer. And because each term hopscotches over the real value, there was this theorem that said basically that the amount of error you've got, like after a given approximation, like after the third approximation, where you go 1, 2, 3, after this approximation, the furthest away you could possibly be from the real value is the value of the next term. Because by then you will have overshot the real value again, and you'll start coming back the other way. So there's a theorem that says that if you want to know the error in a P5 approximation, the answer is the sixth term of the series. So in the case of this one, I just flat out gave you that the P3 approximation, sorry, this is the P5, the fifth degree approximation of sine is this formula right here, and it's 0.259. So the question is, once we've plugged and chugged and got 0.259 for the sine of pi over 12, how far are we from the real value? And it turns out, because this is an alternating series, all we have to do is find out x to the 7th over 7 factorial, which would have been the next term, because the x to the 6th term is 0. So the x to the 7th term is the one that's going to be this little hopscotch back, and that's the most the remainder could possibly be. So we plug in x to the 7th over 7 factorial. X is still pi over 12. 7 factorial is a ridiculously large number. It's like over 1,000. So anyway, this gets really small. So it turns out that the error, the remainder, is around 10 to the minus 8. So that's 8 decimal places, which is pretty crazy. And that just goes to show you how accurate the approximations are when we're close in. So in the next chapter, we'll talk about power series and radius of convergence. So what's going to happen is when you're approximating something like sine, sine goes up and down, right? It goes like this. So if you're looking at the Maclaurin series approximation of sine, it's probably a pretty good fit as you go along here. But then it's going to be really hard for a polynomial to follow this exactly, all these swoops and dives, right? So what's probably going to happen is your approximation might go like this, and then it goes like that or something crazy and just shoots off and totally misses this last jag. Or maybe it's just a polynomial that kind of follows this trajectory okay and then shoots off like that. So basically, the Maclaurin series for sine is only going to work kind of right in this little area near the origin. As soon as we get over here, we're sort of off in no man's land. So that's why the Maclaurin series is only good for a little while, and that's why we're going to talk about radius of convergence later. But when you're in that neighborhood, and when you're in the neighborhood of where that approximation is still pretty good, then in an alternating series, this is how you find the error. It's just the remainder. All right, so this time we'll find the actual error, and it turns out this is easier than it sounds. When they ask for the error approximation or the remainder, then you have to use that trick of giving the term past the last one of the series you're actually using. But if they want you to find the actual error, all you need is a calculator. So you type in cosine 0.3, make sure you're in radian mode, but you just type in cosine of 0.3 and then subtract the answer you actually get, and that is your error. So let's take a crack at this. Now I'm not going to bother working out the full series because, like I said, you kind of want to memorize these things. And since we're finding the cosine of 0.3, that's pretty close to 0. So what we're going to use is the cosine expansion, cosine Maclaurin series, which you might want to memorize, which is going to be 1. And the way I remember this is the sine expansion starts with x, the x to the first term. Cosine is all the even power, so it starts with a 0 power, or 1. Now the question is, do I want to start with a negative sign or a positive sign for that next term? Well, if you think about it, doesn't cosine have to be less than 1? Or the most it could ever be is 1. So if I add an x squared term over 2 factorial, didn't I just hose myself? Because x squared is always positive and 2 factorial is positive. So if I do 1 plus x squared over 2 factorial, I just went above 1. That ain't legal. So that means we've got to make this a 1 minus 2 factorial, and that helps. And once you've got that, you just know it's alternating, So you're all set. And we could go to the x to the 6th term. However, we're looking for a 3-term estimate of cosine of 0.3. So all we have to do is just plug in 0.3. So 1 minus 0.3 squared over 2 factorial plus 0.3 to the 4th over 4 factorial. And when I did plug this into the calculator, I get 0.96593. All right, so that's the approximation. And the actual is 0.95533. So just subtract those two to get your error, and you get 0.0106. All right, so pretty good stuff. The actual and our guesstimate after 3 terms was only off by 0.01, and that's more accurate than you probably would, memorize most things. So not bad. All right, last one. Let's just find the approximation of e to the 1.1. So there's a P2 approximation, so that means I only have to go out to the x squared term, and then the e expansion I don't have memorized. And besides, we can't use the Maclaurin series on this one because this is e to the 1.1. Maclaurin series are centered at 0, right? So if I was finding the e to the 0.1 like we did earlier, then by all means use the Maclaurin series because 0 is really close to 0.1. But by the time we get to e to 1.1, it'd be a lot better to use a series that's centered at 1 instead of 0. So that means I really do need to find a new series. So I'm going to do c equals 1. And let's do our usual thing here. So f equals e to the x. F prime is also e to the x. F double prime also e to the x. So that's nice. And double prime is all I'm going to need because I'm going out to the 2nd degree term. And 2nd degree has a 2nd derivative and all that. Alright, so that means that e to the x. So f of 1, since I'm centering at 1, I need f of 1, which is e to the 1, plus f prime of 1, which is also going to be e to the 1, times x minus 1, plus f double prime of 1, that's also e to the 1, over 2 factorial, times x minus 1 squared. Alright, so it's that quick to come up with the 2nd degree Taylor series around 1. And then, I could just start plugging and chugging. I could just plug in 1.1 for all my x's here. Or if you really wanted to make it more organized, you could factor out the e from each one of these. So you get e times 1 plus x minus 1 is 0.1. 1.1 minus 1 is 0.1 plus 0.1 squared over 2 factorial. And we do all that, we get 3.0037. Alright, and then if you wanted to know what the actual and the error was and stuff, for actual, my calculator, maybe yours will give you a different number, I hope not. I hope we agree. I don't know who's right and who's wrong. So I got actual of this, which is obviously really close, and once again the error is very small, 0.000166. So we're out in like the 4th decimal place of accuracy. Alright, so hopefully that makes sense. Once you practice these Taylor series, they seem really difficult and really complicated at first, but once you figure out there's just plug and chug every time, it's almost like you don't even have to think about it. Just plug and chug mindlessly. That's kind of where you want to be. And if you're really going, to ace the test, you're going to want to memorize some of those Maclaurin series so that you can just whip them off the top of your head. You won't be able to memorize the Taylor series usually because Taylor series could be anything. The Taylor series for e to the x centered around 1 had an e here, but the Taylor series centered around 2 would have an e squared here. And of course, everything else here would be like x minus 2 instead of x minus 1. And the sine and cosine ones are a lot worse because the Maclaurin series for sine and cosine, they only have x's. So the sine series was like x, minus x cubed over 3 factorial plus x to the 5th over 5 factorial. Very simple. We didn't have any even powers of x, but that's because it was centered around 0. So the sine of 0 terms all went away. But as soon as you tried to center that series around pi over 3 or pi over 4 or some number other than either 0 or 90, you're going to get in trouble because now you're going to have every term of your Taylor series. So you're going to have a lot of square, for example, if we wanted to find the sine x thing centered around pi over 4. So now f of pi over 4 is going to equal root 2 over 2. F prime, which is cosine, is also going to equal root 2 over 2. And then f double prime is going to equal negative root 2 over 2. But the point is you're going to have this Taylor series with a square root of 2 over 2 in every single term. So it just gets more ugly and complicated, and that's why when you're doing a Taylor series, you really need to derive it each time. It's just if you're finding a Maclaurin series, or estimating something you need the Maclaurin series for, like the ln of 0.1 or the or e to the 0.1 or whatever, where the Maclaurin series is used, then memorization can help you. And that's why they only have you memorize the Maclaurin series, not the Taylor expansions.